let's talk about compounds with actual functional groups. So first of all, let's define what is a functional group. May or may not contain carbon, always contains other nonmetals. So, for example, in our conversation today, we're going to talk about alcohols and phenols, right? So hydroxyl will be a functional group, okay? The difference is that in phenol, that hydroxyl group is bound to the benzene, to the aromatic compound, rather than aliphatic compound, okay? Compounds that do not contain aromatic cycles, like benzene and others, are called aliphatic, okay? I'm going to let me put the spelling here. So these guys will be aliphatic, is opposite to aromatic, okay? Phenols contain SH group right here, and ethers contain oxygen that connects to carbons, okay? So our goal is pretty much learning how these compounds are formed and named. So this is just another illustration of the functional groups. Whenever you see on the ball and stick model something that is not black or white, black being carbon and white being hydrogen, you can be sure that, you know, it's some kind of a functional group. So how do we name alcohols? So we look at the name of the corresponding hydrocarbon that has the same number of carbons, let's say methane, and then replace ANE with ANOL, or E with OL, okay? So from methane, we get methanol. From ethane, we get ethanol. Alternatively, remember we talked about the description of so-called like methane CH4 molecule, methyl CH3 substituent, right? So, for instance, if we have an alcohol with a formula like this, let's just continue the conversation. How many carbons do we have in this molecule? 3. So, for 3 carbons, the name of the hydrocarbon is propane, right? So we replace E with OL, so propanol, or we can call it propyl alcohol. The whole idea? Make sense? Okay. So, yes, alcohol, well, we call it alcohol, but technically speaking, ethanol. Ethanol is the safest of all alcohols to drink. Okay, I'm not saying that it's safe because it isn't, but it's the safest. Okay. Well, I don't know. Well, maybe propanol, not as safe. Yes, intoxicating product. Yes. Humans learn this, and now the idea is that they learn this from animals. There was a study recently which I absolutely loved. Turns out that chimpanzees seek fermented fruits and consume fermented fruits. That becomes an equivalent of 2 or 3 pints of beer a day. So they getting buzzed. Okay, they have. So we probably learned, well, maybe we didn't learn this from animals. Maybe we knew this as animals, and the tradition was just kept. Okay. Product of fermentation in nature. Okay, all the food-grade ethanol that, actually, to my knowledge, all ethanol that is produced in the United States is the product of fermentation of corn. Well, corn is milled and whatever, right? Actually, most corn is used for ethanol production in the U.S. And some countries produce so much ethanol that they replace gasoline with ethanol. The example of such country is Brazil. They have enormous sugarcane industry, and they use sugarcane. Basically, if you import a car from Brazil, you won't be able to use it in the U.S. because the engine is not designed for this. You can produce ethanol chemically by the reaction of ethene and water. I don't really know why. Okay. It's a solvent, very effective solvent, because it not only can dissolve nonpolar substances, such as iodine, but it also mixes well with water, which is a polar substance. Okay, so it kind of is both. Phenols, propantriol, this, also known as glycerol. Okay, just check, yeah. So glycerol is a viscous fluid, actually very viscous fluid, which is a byproduct of the conversion of fat into soap. I think I've heard the sort of special service when people undergo liposuction. You can isolate human fat and convert it into soap. It's actually pretty easy. Side product is glycerol. Okay, we're gonna try to make soap. It works most of the time. Okay. Now, unlike ethanol that has only one hydroxyl group, it has 3. So, first of all, glycerol is not safe to drink, obviously. Don't. But it is used in many skin products. For example, during COVID pandemic, I actually made, just for fun, a homemade hand sanitizer. I mixed, because, hand sanitizer was out, I bought the bottom shelf vodka and mixed it with some glycerol that I had. And it worked. Actually, they say skin softener. When I was a kid, my dad was working often he was an engineer and worked with chemicals, and his hands got some beating. Okay? The only skin product he's the old style guy. He was born almost 90 years ago. The only skincare product that he used for hands was pure glycerol. Just had a bottle of pure glycerol. And I realized like how wild it is for an average American. Like, we just had it. I don't know where. Like, we got it somewhere. And that was bringing over and over, yes. Now, when you put the, what's the word? Anti-freeze fluid in a car. Yeah. The cooling system. The coolant. Yes. Thank you. The coolant. The coolant contains ethylene glycol. There are 2 good reasons for it. It freezes at much lower temperatures than water does. So when winter comes, your radiator is not going to explode. And it also boils at much greater temperatures than water does. So it serves as a much better cooling system. It can be used as solvent, yes, but the thing is, have you ever asked yourself why the coolant that you buy at the gas station or car parts store is colored? Because ethylene glycol is not. To make it look unappetizing for children, which I think is completely misguided. Because if I'm a 4-year-old, I have like one brain cell, right? And if I see the liquid that is bright green, I'm definitely drinking it. I would say that it's an attractant rather than, because it's so bright. Like make it brown, then maybe I will give it a thought. The problem is that it is true. It's oxidized because OH groups. We have enzymes that oxidize OH groups. We're going to talk about it. Eventually converting those OH groups into acidic groups, organic acidic groups. And that, basically, this oxalic acid will form crystals in the kidneys and ruin the kidneys. Okay, it is toxic. This is an example of a modified phenol. So let me start with the reminder what phenols look like. So a garden variety phenol is this. Okay? It's a pretty toxic compound. It's an irritant, solid at the room temperature. It starts melting at about 35-36 degrees Celsius. I once tried and held a pellet of phenol between my fingers, and I got small chemical burn. I was curious. Phenol, by the way, phenol was the first chemical that was widely used as a skin antiseptic. I don't know if you've heard the term carbolic acid. Carbolic acid is a water solution of phenol. It was developed by James Lister, British surgeon, and now nobody uses it because it's a very strong irritant. When Lister used it, he used it not only for like pre-op scrubbing for surgery. They sprayed it on wounds, which is kind of insane. Like it burns skin. They just sprayed it on wounds to prevent wound infections. So phenol was for a long time a gold standard of antimicrobial chemicals, and then was modified to generate this bisphenol A. Okay, so bisphenol, and it is a very good inhibitor of bacterial growth. The dark side of this chemical is that it affects human endocrine system in a negative way. So BPA was used to prevent bacterial growth in liquids that are stored in plastic bottles. Turns out it wasn't needed altogether. So now if you have a plastic drinking bottle, like some of you have them, right? You can check even these bottles of plastic water bottles. They all going to be BPA free. Okay, it is banned now. Different essential oils, different smelly stuff. Vanillin. I have no idea what it is. Thymol, probably from thyme. Eugenol, I cannot see from what. Isogen, some spices. They smelly. Okay. By the way, another phenol that you may have heard of, although looking at the audience, I don't think you're old enough to hear that. Have you heard about the compound called triclosan? Triclosan, yeah, not old enough. Triclosan was added, no, seriously, it was added to soaps to make them antibacterial, and eventually turned out that it wasn't particularly effective and all bacteria developed resistance to it. So 7 years ago, FDA recommended not to include it. Just another example of phenols being antibacterial. Thiols. Anything organic that contains sulfur and is volatile, meaning it can form vapors. Stinks is not the right word. Okay? So thiols, like for instance here, trans-2-butene thiol. Okay, so you have this double bond, which makes it butene, makes SH group, which makes it a thiol. This number shows you where SH group is. Any sulfur organic compounds are smelly. You deal with this. I don't know if it's on a daily basis, but pretty regularly. Everybody eats either onion or garlic or both, right? From time to time. You're crying when you cut onion because of sulfur organic compounds hitting your eyes. And that distinct garlic smell is also due to sulfur organic compounds. Okay? So, it is used to detect gas leaks. And if you wonder why, I have, as always, almost always, I have a story. So, what's considered to be the stinkiest compound on Earth is ethyl mercaptan, which is ethane thiol. That's it. Okay? It's very smelly. And when it's concentrated, it smells like shit. It does. Exactly like shit. Pretty nasty. It is added to natural gas that if you're using like propane tanks or if you have a gas stove at home, the smell that you feel is not the gas. Propane, methane, ethane, butane have no smell at all. But very small amounts of ethane thiol are added so you can notice when it leaks. More entertaining story of this happened 1 year before I started college, which now, since I don't give a crap, I like to share when I started college. It happened 30 years ago, when none of you was born. Yeah. So, 1 year before I was told, some idiot decided to make ethane thiol in the lab, which is not particularly hard to do. So he made it in a little test tube, and then realized that there is no stopper in the world that could prevent ethane thiol from escaping the tube. And it was like a lab that like you do, like it was unsanctioned activity, okay? The classroom lab. So his classmates and his teacher started like, why does it smell like shit here? Okay? He realized that he was going to get busted. I know exactly which lab it was. We had OrChem labs, same location. So he ran out of the lab, and there's a men's toilet nearby. So he realized he's not going to open the tube because he didn't want to face consequences of this. He just threw it in the toilet and shut the door. Nobody was there. 5 minutes later, the guy, unsuspecting guy, opens the door of that bathroom to use it. The concentration was so high that he barfed immediately. Like there was not even a thought. It was physiological response. Okay? Now, to give you an idea how penetrative sulfur organic compounds are, when I was in college, my major was chemistry, and our building was a separate building. My friends who studied other majors were in different buildings, and they did not go to mine because they said our building was smelly, which it was, but we got used to it. The only place that I didn't get used to is the whereabouts of the lab that was doing serious sulfur organic chemistry research. It was stinky even by our standards. People who worked there, if they wore the lab clothes, because they had a separate set, they left the good clothes outside the lab. If they were to take a subway in the lab clothes. You know, people who are homeless often, homeless people left the car. Like it was too much for them. The only way to get the smell out of the hair was to shave the head. It is that bad. It never leaves clothing, ever. You cannot just wash it away. Naming, you just take a name of the alkane or alkene, whatever, hydrocarbon, and ethyl. Okay? Now, an important thing here, it illustrates it. So you see that the thiol group is added, it sits on the second carbon, right? So we put 2, number 2, showing that the thiol group is at the second carbon. Ethers, oxygen that connects two carbons. These carbons can belong to chains, be aliphatic, like alkyl carbons, or carbons can belong to aromatic structures. Okay? It's bent. Naming is a bit complicated because what usually you do, you name each part, each carbon group that is connected. So in this case, this is what I mean by that. The name for CH3 is methyl. Okay? Since you have two CH3s, it's going to be dimethyl. What if you have asymmetrical ether? You name one, right? Methyl. Then you name the second carbon chain, which is propyl, and then they put them in alphabetical order. Okay, so you go methyl, propyl, ether. Okay? Does that make sense? Now, yes, ethers can be used as anesthetics, which is not, it's kind of cool. Okay? They're safe, they're not toxic, and just to give you a perspective, are you familiar with the approximate time period when first anesthetics were used? Second half of 19th century. So basically, yeah, so during Civil War in the US, most surgeries, most amputations were carried out without classic anesthesia. It was just alcohol. People got belligerently, well, completely drunk out of their mind to numb the pain. And aseptic techniques during surgery were introduced approximately the same time. Okay? It is known that there are more, during the Civil War, more people died because of the complications of surgeries that were killed on the battlefield. So ether, originally, it was, if my memory serves me well, which it does less and less, I believe the first ones that we used was diethyl ether. Okay? And the surgeon would soak the sponge or cloth with it, put it on the nose, and people would inhale and pass out, and it would work as an anesthetic. You have to obviously keep it on, you know. What do you think was the main problem with ethers? Think about the properties of most organic compounds. Huh? Well, that was an issue as well. They're flammable. I think the ignition point for dimethyl ether is below 100 Celsius. we had a professor, an instructor in my school when I was an undergrad, who had the glass built like reaction thingy exploding in his face because it was ether, and he did not find anything better than smoke nearby. He had a beard, and the reason he wore it because he couldn't shave. All those pieces of glass were stuck in his skin. Okay? So, can we do something about it? About the flammability? Yes. Okay? So, these are various fluorines, or sometimes another term is fluorines. Okay? You can see that all hydrogens in these molecules are replaced with fluorines or chlorines. See that? These guys, these chemicals are not flammable at all. You can safely use them in the lab. I used now, these are usually not used on humans for long-term anesthesia because, you have to do it IV. What if you can't have someone just constantly applying? But they are used in animals. Okay? So, for instance, in animal imaging studies, and I know this secondhand because my wife was doing those studies at some point in her career, there's a chamber that is filled with isoflurane, and you put mouse there, mouse gets knocked out, and then you can take an image because otherwise it would be moving. I did a study in which I had to give mice do the nasal drops. I had to give them the drug intranasally, and mice aren't particularly happy when you handle them and doing that to them. So I had a little Tupperware box with a piece of cloth soaked in isoflurane. So I'll put mouse there, close the lid, wait for like a few seconds, see it knocks out, take it, quickly administer, and release. So yeah, if you're curious, did it happen when the mouse woke up in my hands? Yes, it did. It's fine, you're just losing some drug. We're going to talk about properties, and then we're going to stop. So properties of alcohols. They're flammable, first and foremost. So alcohols can be classified based on the number of, that's going to be number of carbons attached to the carbon that is bonded to hydroxyl group. So let's identify. This is the carbon, the highlighted yellow carbon, that is bonded to hydroxyl group. How many other carbons is bonded to that carbon? Only one. So this is why we call it a primary alcohol. Here, the carbon that's bonded to hydroxyl group also is connected to two other carbons. So this means that it is a secondary alcohol. And finally, in this so-called tret-butyl alcohol, its common name, okay, carbon that forms a bond with OH forms bonds with three other carbons as well, and it's tertiary alcohol. So let's see if you can spot which one is which. So, example A. Which carbon is... Okay, hold on a second. Let me do this. Which carbon... This carbon is connected to OH group, right? Let's identify all of them. This carbon is connected to OH group. And this carbon is connected to OH group. So, in example A, this carbon to how many other carbons? Connected to how many? So, secondary. Example B, primary. And example C, tertiary. Yes. Now, if you think about an alcohol as a structure, right, you can do this. Hear me out. We have alkyl group, like and then we have OH group, right? So alkyl groups are very nonpolar. OH groups are polar. So you have sort of a tug of war between the nonpolar properties of the alkyl and polar properties of OH group. It's all a matter of size. So alcohols with few carbons are soluble in water. Methanol here, for example, has this oxygen that due to its high electronegativity pulls electrons towards itself. And when it does, it accumulates partially negative charge, which allows it to form hydrogen bonds with the hydrogens from other water molecules. Reasonable, right? Now, the more carbons you have in that alkyl group, the more nonpolar properties dominate over polar. So, alcohols with, I believe, more than 4 aren't soluble in water, if my memory serves me well. So yeah, butanol is kind of soluble-ish, pentanol is not. Okay? Does that make sense? Good? So we use, so now let me list some soluble alcohols, okay? So we use, this is methanol, right? This is ethanol. This is propanol. And this is isopropanol. Okay? Now, the cheapest of them all, as far as well, all of them are fairly inexpensive. But we only use isopropanol and ethanol. Well, why? We have a lot to uncover here. We uncovered. What's next? Yeah, we're gonna wrap it up. We're gonna talk about solubility phenols next time. But first of all, why is methanol? Anyone knows? Why is methanol never used in hand sanitizers? If a product of any kind contains alcohol, what will some people, not all people, do with that product? They will drink it. And if you asking yourself what? People drink hand sanitizers? In high school in Russia, I knew how to isolate ethanol from brake fluid, because back then they were based on ethanol. Okay? And it's very simple. It's a physical method. It's going to be drinkable. Not great, but drinkable. So people would drink anything to get buzzed. The problem with methanol is that a very small dose of it, as far as I remember, so cup 2 fluid ounces, guaranteed blindness, guaranteed. And 3 to 4, you're probably going to die. Okay? Now, I'm not sure why propanol is not used, maybe because the production is maybe a bit expensive. So, what about isopropanol? What about this guy? What if somebody drinks hand sanitizer that contains this? First of all, are they going to get buzzed? Yes. But interestingly, that molecule will be metabolized in the liver into acetone. So they will develop. So, is it going to be toxic? Yes. Is it going to kill them like methanol does? No. well, they have to drink a lot of it. Okay, does that make sense? Now, let me finish it up with some, okay. Hand sanitizers, this statement. Those of you who work in healthcare, says used as an alternative to washing hands. Is it though? What is it like? You still washing hands. It's a good complementation. I can give you example because I'm teaching a lot of different classes. Rhinoviruses that cause common cold are impervious to effects of ethanol, or isopropanol. So basically, if somebody sneezes on your hands, you need to wash them. Another virus, which I absolutely adore, have you heard about norovirus? Yeah? You should be proud. It was discovered in Ohio, in the city of Norwalk. Okay? This virus is also absolutely impervious to alcohol. The only way to remove it from your hands is to wash them. So hand sanitizer is complementation of the hand washing procedure. So it kills most bacteria. True. You cannot kill a virus because virus is a non-living object. It inactivates many viruses, such as influenza and coronaviruses, but it doesn't inactivate nor and rhino. Usually 60 to 85. It was shown that if you use low concentration, about 20%, bacteria eventually can become resistant to those concentrations. Highly flammable, sure. May contain triclosan. Not anymore. I just told you 7 years ago. The FDA removed it exactly for that reason. Okay? So on Monday, hopefully after the lab, we will chat about, finish this up because it's not a lot to talk about and we'll finally catch up. So we have finished the conversation on Wednesday with the discussion of phenols. Okay? Now let's talk about the phenols being dissolved in water. As you can see here, phenols can be dissolved in water. They are slightly soluble, and the reason why they are slightly soluble is because they have an OH group. Just like in many acids, it can dissociate in the aqueous solutions, producing hydronium cation and the phenoxide anion. As I mentioned before, phenols used to be used as antiseptics, but because of their significant toxicity, not anymore. Now let's talk about aldehydes and ketones, and we group them together because there's something in common between them. They contain a double carbon-oxygen bond. So you're probably familiar with the acetone being a component of nail polish remover and various chemical cleaning fluids. So both aldehydes and ketones contain this carbonyl group here. So in this carbonyl group, the red sphere represents the oxygen, while the black sphere represents carbon. They are connected, as you can see, by a double bond. And oxygen in this situation is very electronegative. It pulls a lot of electron density to itself, making carbon fairly positive. Okay? So these groups, the carbonyl group, is a dipole. So it has a positively charged oxygen and the negatively charged carbon. This presence of this group effectively determines the chemical properties of aldehydes and ketones. So now listen, if a carbonyl group attached on, so this is the carbonyl group, and this is a carbonyl group. If the carbon in carbonyl group is attached to a carbon on one side and to a hydrogen on another, this is an aldehyde. If this carbon is attached to two other carbons, this is a ketone. Does that make sense in terms of the difference between the two? Okay? Good? So in some cases, when you want to write a condensed structural formula, instead of drawing this carbonyl group and aldehyde at the end of the molecule, you can replace it with this. Conventionally, it is a carbonyl group in an aldehyde. In a ketone, we can just do this instead of expanding the entire structure. Does that make sense to you all? Yeah? Okay. So you can see that this is condensed structural formula, but you can replace an aldehyde group with CHO, and in the formula of acetone you can replace carbonyl group in the center by this. So there are common names, and then there are IUPAC names. So IUPAC names are formed this way. Check this out. So imagine you have this molecule. How many carbons are in it? 2, right? What is, anyone remembers the name of the alkane with 2 carbons? Ethane. Okay? That makes sense? So what you do, you replace the E with Al, ethanol. And this is how you form sort of a proper IUPAC names. However, for the first 4 ketones, there are also so-called common names. For example, 1 carbon formaldehyde, according to IUPAC, it will be methanol. 2 carbons, acetaldehyde or ethanol. 3 carbons, propionaldehyde or propanol. And 4 carbons, butyraldehyde or butanol. Make sense? Okay. So these are effectively formulas, and I want to highlight. So acetaldehyde, formaldehyde or methanol is kind of weird because there's only 1 carbon and it's connected to 2 hydrogens. But starting from ethanol, this carbon is connected to hydrogen and another carbon. This carbon is connected to hydrogen and another carbon. This carbon is connected to hydrogen and another carbon, which makes them aldehydes. Does that make sense? Okay. Now, when we name ketones, we replace the E in alkane to O-N-E. I want to highlight that the smallest ketone has to have 3 carbons. Do I understand why? So, think about an aldehyde. So you have this group, carbonyl group, right? It forms 2 more bonds. You put hydrogens, that's formaldehyde or methanol. Replace one of them with an alkyl group, you get ethanol or acetaldehyde. But in order to connect that central carbon and carbonyl to 2 more carbons, you have to have 3 total. So the simplest, the smallest ketone is propanone, which you see how the name is made. So propane, E is replaced with O-N-E. Okay? It's fairly straightforward, right? Now, when you start seeing differences about the position of the carbonyl group, you have to add the number that would show you at which carbon the group is. So for instance, how many carbons are in this molecule? 5. So bent. Does that make sense? More specifically, pentanone, pentanone. But can you place this group at this carbon instead? What I'm talking about is that formula. You can do that. It's still going to be a ketone because this carbon is connected to 2 other carbons. But the position of the oxygen will be different. So for this one, obviously, this central carbon is going to be number 3, no matter how you count. What should be the name of that molecule then? What number should we give to this carbon? So again? Why? No, we don't. It's not left to right. The molecules don't have left and right. Remember, you always have to have the smallest number. So if it's not 4, then what? Which number? 2. You just have to count from the other side, and it's going to be 2 pentanol. Okay? Make sense? Now, why do we not assign any numbers here? Because if you make a molecule that is, that looks like this, let me get rid of that part. If you make a molecule that looks like this, these molecules, this one and this one, are the same. You just need to turn this 180 degrees and that's it. They match each other. Not making sense. So starting at 5 carbons, you need the number. The smaller aldehydes and ketones can be dissolved in water because highly polar oxygen in the carbonyl group forms hydrogen bonds with hydrogens of water. Okay? So 4 or less. Essentially, you see all the way up to 4, they are soluble. Anything above it? Not really. So, important aldehydes and ketones. Well, acetone or propanone, already mentioned. Anyone ever worked with formalin? Formalin is used to preserve biological samples. It's a solution of formaldehyde or methanol in water. It's very, very toxic. It is very, very stinky. And it kills almost everything. So bacteria, fungi, or anything else, basically these things don't rot. Okay? Several aldehydes are like they have aroma. So the almond, the vanilla, the cinnamon, those aromas are all due to the presence of certain aldehydes. So let's do some classification here. A, aldehyde or ketone. This carbon is connected to what? To other carbons. So you can think of it this way. Listen to the sounds. If carbonyl, carbon, is connected to carbons, it's a ketone. Okay? This guy, connected to one carbon and one hydrogen, what is it? Aldehyde. This one? Aldehyde, yes. Because it's one carbon, one hydrogen. And this one? What is that? What is that? Ketone. All right? So, the reactions. Alcohols burn. Okay? But alcohols also can undergo the process of dehydration. So look at this alcohol. This is ethyl alcohol. Can you see that? So you can heat them up in the presence of acid, usually sulfuric acid, and they're going to lose water, forming a double bond between the carbons. Carbon that used to carry hydroxyl group and the adjacent one. Okay? So you can make alkenes that way. Okay, now this bothers me, the statements. What is oxidation and reduction? Did we talk about it at all? No? Okay. So listen, I'm going to give you sort of a crash course in oxidation and reduction, general. So first, a proper, strict chemical definition of the oxidation and reduction. Look at this. Imagine that you have a compound A. It's too big. So you have a compound A. And you have a compound B. Compound A loses its electron and gives it to the compound B. When it loses electron, A is oxidized. When B gains electron, B is reduced. Now I have a question for you. So I work for Stark State College. Am I being paid for my work? It's a rhetorical question. So I am paid for my work by who? By what? By which organization? Stark State. Or you can say that Stark State pays me. So we have two sides of the transaction, right? Stark State and me. Stark State pays me. I am paid by Stark State. So to continue a little bit here, A is oxidized by what other participant of the transaction? B. And B is reduced by A. Am I clear? Or we can say that A reduces B and B oxidizes A. So A is reductant and B is oxidant. Will these questions be on the exam? No. So you may ask, why do I tell you this? Are you planning on taking any biology classes in the future? Mostly like microbiology. What? Well, who knows? Microbiology, A&P, yeah, maybe. If you can do that, it'll simplify your life dramatically in those classes, especially when you're talking about cellular respiration. Okay? Now, so another way to see whether something is oxidized or reduced is not by checking the electrons. The electrons are going to be transferred anyway, but by checking the bonds between oxygen or hydrogen and carbon. Okay? So this is what I mean. Look at this. When organic molecules get oxidized, they either increase the number of carbon-oxygen bonds, okay, or lose bonds between carbon and hydrogen. And the reduction is the opposite, okay? So, more hydrogens, reduction, less hydrogens, oxidation. Okay? Now, every biologist will tell you that this is the definition of oxidation and reduction. Don't listen to me. They don't know what they're talking about. So, how are alcohols oxidized? If you have a primary alcohol, remember, in the primary alcohol, this carbon is connected to only one other carbon. When you oxidize this OH group, you form aldehyde. Quick question, folks. Compare the molecule on the left, ethanol, to the molecule on the right, acetaldehyde. How many bonds are between carbon and oxygen in the left molecule? One. And how many hydrogens do we have here in that particular group? One, right? One hydrogen, one bond between carbon and oxygen. Now we get to aldehyde. How many bonds between oxygen and carbon? So more carbon-oxygen bonds. And what happened to that, to the hydrogen? We lost it. So less hydrogens, more carbon-oxygen bonds. We just oxidized ethanol to aldehyde. Does it make sense? We can take an aldehyde and oxidize it further. Take a look at this group. How many carbon-oxygen bonds? 2. How many hydrogens? In the group that I highlighted. In the group that I highlighted, 1. Now look at this group. How many bonds between carbon and oxygen? Dude. Like seriously, we counting. 1, 2, 3. Oh, misheard you. Sorry. My dude was not directed. Then it was directed at the group. Okay? So we have more carbon-oxygen groups, which means it's oxidized. So, in a nutshell, primary alcohol is oxidized to aldehyde, and aldehyde is oxidized to a carboxylic acid. Good? Now what about secondary alcohols? In this case, this carbon is trapped between two other ones. So when OH group is oxidized, it forms a carbonyl group, right? But this carbonyl group is now in the middle of the molecule, so it's going to be ketone. And that's it. You can't oxidize ketone further without destroying the carbon chain. So secondary alcohol is oxidized to ketone. We're good? What? I'm anticipating a very interesting conversation in the future. When you have a tertiary alcohol, this carbon has no hydrogens to lose it. Like you have to break one of these bonds. So you can't oxidize a tertiary alcohol without destroying the carbon chain. Does that make sense, y'all? Which brings us to one of my favorite conversations. We're going to start with methanol poisoning. Remember we're talking about hand sanitizers last Wednesday? So if a person drinks methanol, it is oxidized in formaldehyde, extremely toxic compound that if like person drinks enough methanol, will kill that person. And then methanoic acid, which also is not. By the way, you know where you can find methanoic acid? In ants. Fire ants, when they bite you, that burning sensation is methanoic or formic acid that goes in your wound. And you probably may guess how formic acid was first obtained from nature. Yes, they got a bunch of ants, put them in a flask, and heated them up, and evaporated formic acid out of ants. Okay? Does that make sense? What these chemists don't tell us is how methanol poisoning is treated. In order to push methanol out of your system, people who have this condition and are brought to the hospital, they given copious amounts of ethanol. So physicians flush, literally, like they fill them up with ethanol. Ethanol pushes methanol away, and then you're treating a person who has very severe alcohol intoxication. which is doable. Okay? Which brings us to ethanol. It is a depressant. It is the most dangerous drug known to humans in terms of deaths. Okay? You can analyze the alcohol content with a breathalyzer, and people who drink a lot metabolize ethanol much faster than a social drinker, like a couple of glasses of wine once in a while. Okay? Now, I was anticipating that. Like, few biological aspects. In your body, there are enzymes. When somebody drinks alcohol, it is first oxidized to acetaldehyde, and then, which they missing a big point here I need to insert, it's not carbon dioxide, it's acetic acid first, and then carbon dioxide. Am I making sense? So first of all, when you drink a lot of alcohol and it's being processed, you develop temporary acidosis. You produce acetic acid, vinegar. Second, which organ metabolizes ethanol? Come on. Huh? Liver. Yeah. Now, if you keep hammering your liver with alcohol, will it give up? In the evening, it will say, yeah, screw you, I'm not doing anything. So it will oxidize ethanol to acetaldehyde and then stop. And you will have acetaldehyde in the circulation. And this is what gives you, this is the part of a hangover, because acetaldehyde is toxic and you feel crummy. Does that make sense? Now, people genetically can produce different levels of the enzymes that metabolize alcohol. So some people are more resistant to it. Okay? Now, are you familiar with one of the main killers for the Native Americans when European conquistadors came to Americas? It was booze. People of the Asian ethnic origin, and they are of the Asian ethnic origin, similar to Japanese, Chinese, those folks, they produce very low levels of this enzyme, so-called alcohol dehydrogenase, which means they don't break down alcohol, and they get drunk extremely fast and get addicted very fast. Okay? You can look up Tokyo office workers on a given evening. They are hammered, like absolutely hammered, like sleeping in the subway on the floor hammered. They have very low tolerance to alcohol. Okay, so it's a genetic. Also maybe, I mean, if somebody drinks a lot, eventually gets strained. Now, oxidation of thiols. So here you can see a thiol, okay, two thiols actually, that are a part of an amino acid called cysteine. When they are oxidized, the hydrogens are removed and they form this disulfide bond. Now, I want to highlight something. Hear me out. This is a protein chain. This is a protein chain. They were independent, and now they are connected. So understanding that two SH groups can form this disulfide bridge is important to understand like why this is critical in shaping protein molecules. Okay? Okay, different. Does that make sense? So I want to highlight a couple of things. The processing of alcohol is different in different people. Okay, this is a very average. Okay. So just, it also, as you can imagine, it depends on the pace. And I'm not being like funny, I'm being realistic. It depends on the pace. If you down a bottle of vodka in 1 minute, that's going to be harsh. Okay? But if you spread your alcohol consumption over a longer period of time, it's going to have different effect. Okay? Also, it depends on the context, so to say. If you are sitting, it's known fact that if you drink and then do some mild activity, let's say you drink and you walk, increased metabolic rate that you have speeds up the metabolism of alcohol. Okay? Food that you consume, it doesn't prevent alcohol from being absorbed, but it may slow down the absorption. Okay? So one of the examples of the pace versus this data, I know a guy, like he's a friend of mine. So far, in our midst, he holds a record in the beer consumption in 1 day, from 9 a.m. to 9 p.m. It's 8 liters. It's more than 2 gallons of beer. Okay? So by these standards, he should be dead. No, he's not. He's a bit fat, but not dead for sure. Okay? So, and again, they were walking around the city, having a pint here and there. So, yeah, of course, he's Ukrainian. Okay? And again, depends on the person and genetics. Even genetics, when I have a brother, when I was growing up, there was no legal age, drinking legal age in Russia. Like, you could drink at any age if you have access. So when I started socially drinking, my brother and I, we would drink. He would bail very quickly, because he didn't feel well, and I would be fine. Even us, we had considerable genetic difference between the two. Tollens test, or the silver mirror test, tests for the presence of the carbonyl group in the aldehyde. So basically, you mix an aldehyde with the reagent that contains positively charged silver. Silver oxidizes an aldehyde to ethanoic acid. And when silver oxidizes, it is being reduced. So you have a thin layer of silver on the inner surface of the tube. It's a pretty cool test. Okay? Another test that is used to determine certain aldehydes is the Benedict's test. So in Benedict's test, check this out. This group, aldehyde or ketone, based on what we've learned. This group, the highlighted, aldehyde or ketone. Aldehyde. And then there's a OH group nearby, actually adjacent. Make sense? If you mix it with a Benedict reagent, which is blue, this copper will oxidize this aldehyde group, formed an acid and a brick red solution of the copper 1 oxide. And I think we're going to do it on the very last lab on December 1st. It is used to test for very specific type of sugars, so-called aldoses. An example of an aldose is a glucose. So you can see the Benedict's reagent mixed with glucose solution on the left. You heat it up, you have to boil it. The aldehyde is being oxidized to the acid. You have gluconic acid and the brick red copper 1 oxide. Okay? Now, just like you can oxidize aldehydes to acids, or you can oxidize alcohols to aldehydes and ketones, you can reduce aldehydes and ketones back to the alcohol. So look at this. Aldehyde or ketone. Aldehyde, you reduce it using hydrogen. Why is it a reduction? How many carbon-oxygen bonds are in here? 2. How many carbon-oxygen bonds here? So less. How many hydrogens are in this group? 1 hydrogen in aldehyde. How many hydrogens are here? 3. Does that make sense? So when you reduce an aldehyde, you get a primary alcohol. When you reduce a ketone, you get a secondary alcohol. Make sense? So, let's figure out. This OH group is about to be oxidized. This is alcohol, primary or secondary. This carbon is connected to how many other carbons? So secondary. When the secondary alcohol is oxidized, what does it form? A ketone or an aldehyde? That's the answer. Make sense? This primary or secondary alcohol? Primary. So when it is oxidized, okay, what should it be oxidized to? Well, okay. This guy is oxidized to what? Primary alcohols are oxidized to aldehyde, and this is your aldehyde, right? You have more carbon-oxygen bonds. And then aldehyde is oxidized to what? Dude, you gotta look for a similar structure. Which structure is similar to number 3? Like seriously similar. Number 4. So this will be propionic acid. Okay? Clear? Awesome.